There we go. 1.3. 1.4 is next time. Quantifiers. Existential and existence and uniqueness. That's what we're talking about. Let me put this on full screen. So let's go look at our definitions. A sentence which contains variables is called an open sentence or a predicate and becomes a proposition only when its variables are assigned specific values. So when you know what the variables are, then it becomes a proposition. So when P is an open sentence with variables x1 to xn, we usually write the symbol P x1, x2 all the way up to xn, comma delimited. We're actually not really going to use the symbol much, but when you see it, that's what it means. It means that it's a proposition. Well, it means that it's an open sentence. The collection of truth objects that may be substituted to make an open sentence a true proposition is going to be the truth set. The collection of objects that make your proposition, your open sentence true, is a truth set. The universe of discourse is a set of objects available for consideration for the truth set of a sentence. And then with a universe specified, two open sentences are equivalent if they have the same truth set. So they're going to be the same if they have the same truth set on them. Let's look at some examples. Consider the sentence x plus y equals 3z. Determine the truth value of P453. So tell me about P453. What is that when you plug that in? Yeah, you have 4 plus 5 equals 3 times 3. That's true. Tell me about P1, 2, 4. Yeah, 1 plus 2 is not equal to 3 times 4. So that one's false. And I'll put false up here. Now let's look at example 5. Find the truth set of the sentence P of x, x squared is less than 5, when A, the universe is the natural numbers. Remember, the natural numbers are the set 1, 2, 3, keeps on going like that. So in the set of natural numbers, which ones have a square smaller than 5? In part B, we're talking about the integers. The integers are the set negative, positive, and they include 0. So which values there have a square less than 5? Now for part C, that's all the real numbers. Which ones there have a square root less than 5? It is. Sorry, it's not going to be, it's going to be a parentheses. It's going to go from minus square root of 5, right? To the square root of 5. This is an open range. Well, you have to solve x squared less than 5. So when is x squared equal to 5? Plus or minus square root of 5. And then it's everything in between there. You could also write that as minus the square root of 5 less than x less than the square root of 5. Those notations are interchangeable. Can we do that? You have homework problems like that. Back to basic arithmetic. We like those days. Determine if the sentences 3x plus 2 equals 20 and x equals 6 are equivalent open sentences under any number system. So that would be under the integers, under the naturals, under all the number systems. So what is the truth value of x equals to 6? What values give you that? What values for x make that true? 6. What values make this one true? So 3x equals 18. So what is x equal to? 6. Are they the same? So that means they're equivalent open sentences. Yeah, so we would usually write this p of x, and then that would be 3x plus 2 equals 20. So yeah, the equation is a sentence. And then this one would be q of x, x equals 6. Yeah. So tell me about example 7. Determine that the sentences x squared equals 4 and x equal to 2 are equivalent open sentences in the universe of the reals. No. Solve the first one. X squared equals to 4 tells you x is equal to plus or minus the square root of 4, which is 2. And then this one over here is x equals to 2. So this set we have minus 2 and 2, and this set is 2 only. They are not equal, so that tells you they're not equivalent. Can we do that on our homework? Okay. Now, the whole point of this section is existential quantifiers, and existential means exist, there exists. So you have a existential, I forget what the other one's called. I should know it. Universal, existential and universal. The existential quantifier simply means there exists. There exists something that satisfies some condition. So for an open sentence P of x, the sentence there exists an x P of x is read, and there exists an x such that P of x, or for some x P of x. This sentence is true if and only if the truth set of P of x is non-empty. We use this capital backwards E, backwards capital E, however you want to describe it, to mean there exists. You can find this in your LaTeX stuff. So you can actually find that symbol there. An open sentence P of x does not have a truth value, but the quantified sentence there exists an x such that P of x is true does have a truth value. One way to show that it's true is to identify an object in the universe so that the proposition P of that object is true. To show it's false, you have to show it's false for every object. So that's where we're headed. Let's go do some examples. How would you verify that this sentence, there is a prime number between 5060 and 5090 is true over the natural numbers? What would you have to do to verify that that is true? Test it out. Test it out, meaning find one that works. Find a prime number in the given range. Now, when you're writing this in a proof format, these ones are the hardest ones to prove, but they're the easiest ones to write, because once you figure out what works, you simply write, note that whatever you chose works, conclude, you're done. They're very short proofs to write. They're some of the hardest ones to actually do because you have to figure out the value that actually works. Finding that value that works is not always easy. Okay, so literally find a prime number in the given range, verify that there exists one in that range. That's all you're doing there. Determine the truth values of the statements for the universe are. There exists an x so that x is greater than or equal to 3. Can you find an x in the reals that satisfies that? 4. So this is true. Since 4 is in the reals, and 4 is greater than or equal to 3. This forward-facing, funky-looking thing is called element of. So 4 is an element of the reals, 4 is greater than or equal to 3. So this one is true. Tell me about the next one. There exists an x so that x squared equals to 0. Can you think of a real number whose square is equal to 0? 0. Oh, with my computer. Since 0 is in the reals and 0 squared is equal to 0. So it works. Notice that's the only value in the reals that works. Every other value you're going to get a positive amount when you square it. Tell me about part C. There exists an x so that x squared equals minus 1. False. Since for every real number, the square is positive. Oh, I'm putting greater than or equal to 0. Can we do that on our homework? Maybe. You're looking around funny. I'm asking everybody, can we do that on our homework? Can we do these ones? Yeah, maybe. Okay, show that. What did I tell you show meant? Prove. So we have to prove this. Show that there exists an x squared plus 2x plus 1 equals 0 is true in the universe of real numbers. So we're going to write our little proof symbol. What value? Let's go do our scratch work. We have to find something that works. Find something that works. I'm going to give me a little more room. Okay, so if we do negative 1 squared plus 2 times the negative 1 plus 1, that's going to be 1 minus 2 plus 1. What is that equal to? 0. So that works. So now we're going to come over here and we're going to say now.
So in the homework, you need to take the
Yeah, well, when you do the begin proof, so suppose you had done this backslash begin proof. It'll put the begin and end symbol on it for you. Recompile it, you'll see it there.
and we'll have homework. And that's when you do the proof, you're reading proof when it's a show.
When it's a show or a prove or
When it's not on the table.
Yeah. Okay, so we're going to say now, and then you're just going to put this on your display centered, which means use a backslash math display symbol. But I'll just write it up. So you have 0 squared plus 2 times 0 plus 1 is equal to 0. And 0, notice it says the universe is the real numbers. Thus, that's Blackboard. Bold. You have to go to font. You can actually just use a boldface R and that works too. Yeah. But that's how you do that funky looking R. It's just bold and I can't write bold, so I do a double line there. But you can find it where it's a double line in some books, and some books it's just bold, and some books it's just R. Yeah. So thus, the statement is true. I can put the period at the end of true. So notice how big my proof was. It's very short. Question. Oh, I'm supposed to be putting in 1. I already forgot that. Minus 1 squared plus 2 times minus 1 plus 1 is equal to 0. I saw the 0 at the end, and that's what I was working off. Yeah. Minus 1 squared plus 2 times minus 1 plus 1 equals 0. And minus 1 is in the reals. Those are the two things you have to check. Does it satisfy the equation? Is your variable in the universe? If those both hold, then you have your proof done. So this is essentially 2 sentences. Very short to write, can be somewhat tedious to solve, because sometimes they're just guess and check. Notice that you could have actually solved that by factoring your equation as x plus 1 quantity squared. Okay, let's look at another one. Oh, universal quantifiers. I took the next example out. Universal quantifiers mean for all. So this would be for all x, p of x is true. And that means that p of x has to be true for the entire universe. So to show it's false, so to show for all x, p of x is false, you find an x in the universe so that p of x is false. Let's go look at examples. Determine which of the following is true for the universe of all real numbers. For all x, x plus 2 is bigger than x. Yeah, this is true. If you add 2 to something, it's going to be bigger than what you started with. This is true since 2 is bigger than 0. Now, we'll talk more about this idea in abstract algebra and why it actually works. But until then, we can assume we know it. That'll be next semester, fall semester. You guys will be taking that class. For all x, x greater than 0, or x equals to 0, or x is less than 0. Can there be any other option for a real number? Positive, equal to 0, or negative? That's everything. No, it says for all x, these are ors. X is either positive, x is equal to 0, or x is negative. That's true, right? This is actually called our trichotomy law. The only 3 options for the real numbers. Let's look at the next one. For all x, x is greater than 3, greater than or equal to 3. No, that's false. If it's false, you have to tell me a value where it fails. So give me a value in x value. 2 is less than 3, and 2 is in the universe of the real numbers. So it's a false statement. How about number 4? For all x, the absolute value of x is bigger than 0. Careful. Tell me about 0. It's 0. Absolute value of 0 is equal to 0, and 0 is in the reals. That one's tricky because you don't think about 0 being plugged in for your variable for x. So first 2 are true, the last 2 are false. You're going to have several of these on your homework. Be careful when you're looking at them because they're a little tricky. So make sure you ponder it well and make sure that you think through all the options that you could plug in before you decide whether they're true or false. If you can factor something, it's not prime. Keep that in mind. That's going to be coming up too on one of these homework assignments. They're going to give you a polynomial that you can factor and they'll ask you if it's prime. And it can't be prime if you can factor it. Okay, notation. In general, a sentence of the form all P of X are Q of X is symbolized for all P of X. If it is P of X, then it is Q of X. P implies Q. So whenever you see all P are Q, think this form. If you see some P are Q, then there exists an X, P of X, and Q of X. These are confusing because when you actually read this sentence, you don't think that's exactly what they're saying. But that's the notation that we have taken it to be from math for clarity. So when we see that, that's what we know it means. Okay, so now let's go look at examples. Write the sentence, all large red apples have spots, symbolically. Assume the universe is a set of all fruit. So this is all something, have is the same as are. So are spotted, have spots, same type of thing. So what form should that be? That should be the first one. Do we remember what it looked like?
How do you say that upside down? Is that the universal?
Yeah, that's universal. It's for all.
Read it?
For all. Mm-hmm.
Like for all and then P of X. If P of X.
Then Q of X. Mm-hmm. So we're looking for all X, P of X implies Q of X. Now, what is P of X? Large red apples. So we're going to have, let me write it this way. I'll mix math and English. For all X in the universe of fruit, for all fruit X, maybe I'll write that down too. For all fruit X, if, I'm just going to write it this way. X is large, and X is red, and X is an apple. And we use a square bracket instead here. That implies X is spotted. That's the answer. Mm-hmm. X is large and X is red and X is an apple implies X is spotted. So you break up any modifiers by the and statement. And you're going to group them together before your implies. So, tell me about number 18. Write the sentence, some large red apples have spots symbolically. So some is what? Yeah, there exists an X, P of X, and Q of X, right? So let's write this down. There exists fruit X. P of X is going to be X is large, X is red, X is an apple. X is large, and X is red, and X is an apple. And what does that go in? X has spots. That makes sense? Mm-hmm. That's how we do those. You can have a few of those on your homework as well. Practice problems. So let's see. I'm 1, 2, 3, 4. So we have 4 of them, 2, 4, 6. So you guys back, you're going to do number 1. In the middle row, get number 2. You guys get number 3. And then we'll do number 4 at the end. Do them together so you guys give me one sentence together.
Can you go back to
Two slides before, or
Oh,
just
no. Okay.
this one?
Make it sweeter.
Oh, wait. Why do
I guess we could order them.
Then you have to define which variables.
If you don't have that, you'll just start in it.
Right.
Yeah.
Right.
Mhm.
Good.
You're a math major, right? Physics? Oh. That's even harder in my opinion.
There's not a lot of math education. So like, next semester, when I'm taking the online stuff, I was talking to Mr. Fuentes today, and I'm gonna be the only one in class.
And hopefully you don't have to leave early then, right?
Yeah. So, he said it's probably just gonna be me and him, unless if there's like new students
Coming in.
coming in that aren't math education. And I guess there's like, they have a class right now, and he wanted me to take it, but it's during this time. So I
Oh,
couldn't
yeah,
take it.
couldn't take it, yep.
So,
And they offer that every semester, I think, don't they?
yeah, that's what mine says, like, they offer it whenever needed. So
Gotcha.
like, if I was like, I need it, then you would take it. But it's just funny, because I think most education is elementary.
Mm-hmm, mm-hmm.
And then after elementary, it's like English. English is pretty big, from what I've heard.
We actually have a slump right now, math majors. Last May, we graduated
Yeah, like Adam McQuiston.
12 people or something like that. It was like everybody left. So we're waiting to get another group coming in. Mhm.
Adam was lucky this
Did you ever, Tom?
Yes, I had him in class years ago. Mhm.
Yeah, I have. He was a senior. Well, he was a senior. I
Yeah.
think he was like a super.
He took a bunch of classes. It was like,
Yeah, he told me. to-
yeah, he did. And he took some business classes too, I think. Okay, so,
But you
so
had a lot of classes.
very sharp kid, very sharp kid.
Right, I know.
Yeah.
I went to.
Oh, awesome. Yeah. The whole family is very outgoing. Okay. The first sentence, back row. What'd you guys decide? What's the symbol? Is that the upside down A or the backward G? Upside down A. And so then for every odd prime, what is your universe? Here's the real numbers. For every real number X, then what comes after that? X is, actually let's break it up. X is odd and X is prime. And X is less than 10. Imply what? Is prime. Okay, middle table. Upside down A or backwards E? Backwards E. And so you have X is a real number, so real number X. There exists a real number X. And then what do you have? Now we have a real number there. Okay. Oh, the universe, that, so it's there twice. Okay, yeah, we'll put it there. X is a real number. And so I'm going to write that in symbols just so you see what that is. There exists a y. X times y is equal to 1. That's what it means to be a multiplicative inverse. No, you can write is a multiplicative inverse. But I'm just showing you how you would write that in symbols. You can do that either way. And then front row, what'd you guys do? Upside down A, backwards E. Backwards E. So, and in yours, X, well, first of all, real number X because that's the universe.
Did you put real number on integer?
That's going to go inside because it specifies the universe up here. That's what goes outside. So for every, there exists a real number X, and then X is an integer, goes inside, and X is even. And then what do they say? Even in some, okay, notice that this and right here kind of breaks this up. Some integers are even and some integers are odd. So there exists a real number, X is an integer and X is even. It's a different X. It says some integers, you're getting another variable right there. So you had some integers, there's your variable right there, and now you're getting another variable right there. So there exists real number y. Y is an integer, and y is odd. And notice that the and goes between the two of them. I could actually take the there exists a real number y and there exists a real number x and keep them outside. I could do that. Or you can keep them grouped with where they're needed in the definition. You can do it the way I did it here. Or you can take both of those, there exists a real numbers x and y out in front of everything. Now, number 4 is the hardest one, and you have one like this in your homework. It says, write the definition of a rational number in symbolic form. You aren't going to have a rational number. I think you have to use continuous number or limit or something like that. So the question is, where do you get it from? And the answer is, look at the preface to the student, that first part of the book before chapter 1 begins. They will have the definition that you're looking for your homework. So if you just read through it, if you have your, I don't know how many of you brought your books today, but if you look at the front of them, they'll have them in bold. So you're looking for the bold terms that have what you're looking for. And so I'm looking for the definition of a rational number. That would be in the middle on the page XVI, yes. And you see rational in the paragraph there, and then it's got the whole thing on it. And that's what I wrote down right up here. The real number x is rational if and only if there are integers p and q, q not equal to 0, so that x is equal to p over q. And we want to write this in symbolic form. So let me tell you where this is in the book. This is going to be on the bottom, page 22, if you're following along in your textbook. I lost my page. So we're trying to write the definition down. So let's begin. The real number x is rational So I'm just going to write that part down. The real number x is rational if and only if. That is our biconditional arrow is the same thing as if and only if. Now here we go. It says there are integers. So there are is our capital backwards E, backwards capital E. So there exists integers P and Q. With the property Q is not equal to 0 and X is equal to P over Q. So you're really turning the last half of it into symbols. Does that make sense? Yeah. The first part, you have to just write that first part down. Any questions on that? Okay. Equivalent sentences. Two quantified, what does quantified mean? Means there exists or for all. Two quantified sentences. It either has there exists or for all, are equivalent in a given universe if and only if they have the same truth value in that universe. Two quantified sentences are equivalent if and only if they are equivalent in every universe. Okay? To be equivalent, they have to be equivalent in every possible universe. To be equivalent in a given universe, they have to have the same truth value in that universe. So they either have to be true or they have to be false. Let's look at example 21. Are the sentences for all x, x is bigger than 3, and for all x, x is greater than or equal to 4, equivalent in the universe of integers? So is this one true or false in the integers? Can you think of an integer that's smaller than 3? 2. So that would be false because it says for all. How about for all x, x is greater than or equal to 4 in the integers? 2 is still in the integers and that doesn't work. So they have the same truth value. They're both false, so they are equivalent. They are equivalent in the integers. Now, are they equivalent in the universe of the natural numbers greater than 10? So you can only restrict yourself to like 11, 12, 13, 14, 15. Are they equivalent in that? Yeah, they're both true in that space. So that means, yes, they are equivalent there. Are they equivalent in the universe of real numbers bigger than 3.7? No. No. For real numbers bigger than 3.7, the first one would be true. X greater than 3 is true. But, oh wait, they would be, right? X greater than or equal to 4. No, they'd be false. Because 3.7 is smaller than 4. So they are not equivalent in that universe. In general, are they equivalent? Are they equivalent in every universe? No. So they are not equivalent sentences. Okay, for them to be equivalent, they have to be equivalent everywhere. Look at example 22. Are the quantified forms there exists in x, p of x, and q of x, and there exists in x, q of x, and p of x equivalent? Tell me about p of x and q of x. Well, first of all, before we do the p of x and q of x, tell me about p and q. That's identical to q and P. The order doesn't matter for the and. So if this is true, then that is true. So yes, these are equivalent. Because switching the order of the and statement isn't going to change anything. That makes it equivalent. Now, tell me this one. There exists an x, P of x implies Q of x, and there exists an x, Q of x implies P of x. Are these equivalent? No, the order matters here, so these are not the same. So that means these are not equivalent. Order matters on implication. Okay, you have homework problems like that. Can you do those? I hope. Okay, we have a theorem here. It says if A of x is an open sentence with variable x, then the negation of for all x, A of x is equivalent to there exists an x, not A of x. Well, we could, except we don't know when that is true or false. So we're actually going to do a proof the other way. So our hypothesis is A of x is an open sentence with variable x. That right there. Let A of x be an open sentence with variable x. Now for the first one, we want to look at not for all x, A of x. And we're going to assume that that's true, because for it to be equivalent, it has to have the same truth values. So we're going to assume not for all x, A of x is true. Well, if not for all of x, A of x is true, then that means that if you take away the negation, for all x, A of x has to be false, right? Do we all follow that? It's because of the tilde in front. The tilde says negate. If the negation of something is true, then the original value has to be false. So that means for all x, A of x is false. Well, if A of x is not true for every x, that means that there exists an x so that A of x is false. I better write it in words first before I confuse you with the symbols. And so there is an x such that A of x is false. Now, for that particular x, I have then not A of x is true. Because A of x is false, so not A of x is true. Thus, I have shown that there exists an x, not A of x is true. Now, I assumed that this one right here was true. I got to this one right here is true. So they're equivalent statements. We use our vertical lines, 3 of them, to say equivalent. This is for part A. Let's do part B. We have the same assumption for part B. Let A of X be an open sentence with variable X. We're going to let not the existent X, A of X, be true. So then tell me, if the negation is true, what is the original? The existent X, A of X is what? False. If the negation is true, the original one had to be false. So there exists an X, A of X is false. What does that tell you? If I'm saying there exists an X so that A of X is not possible, that means you can't find an X to make A of X a true value. And so, for all X, A of X is false. Thus, for all X, not A of X is true. And there's our final statement. That's the same thing. This was the truth that I started with. This is a truth statement that I ended with. So I know the equivalent. Thus, not there exists an X, A of X is equivalent to for all X, not A of X. Now, what you're taking away from this is not so much the proof. Those have never showed up on tests yet. Doesn't mean that they won't, but they haven't showed up on tests yet. But take away what it says. If you want to negate a for all, it becomes a there exists. And then you have to negate the sentence afterwards. If you want to negate a there exists, it becomes a for all, and then you negate the sentence afterwards. This is what we're going to call a useful denial. This is the last part of our homework. So let's do examples. Give a denial of, this is horribly long, for all X, there exists a Y, there exists a Z, for all U, there exists a V, and a whole bunch of stuff. So we have to, I'll write it out. For all X, there exists a Y, there exists a Z, for all U, there exists a V. They're just trying to make it long and complicated. So negating all of that means I have to change each of these. What does for all become then? Yeah, there exists, or for some. And then what does the there exist become? For all, those are Y, for all of Y. Then what does the there exist become? For all Z. For all becomes there exists a U. There exists a V becomes for all V. And now I have to negate this whole thing. Well, when you negate something with an inequality on it, that's going to become less than or equal to. So then this becomes X plus Y plus Z is less than or equal to 2U plus V. That makes sense. This is actually a very important process for us to be able to do, because sometimes it's easier to prove the denial of something than the actual statement itself. And so we need to be able to do the denial of it Because if we can prove the denial is true, then we know the original statement is false. So this is going to be one of our tools of proving things. Okay. For the universe of all real numbers, find a denial of every positive real number has a multiplicative inverse. So let's write it symbolically first of all. Every positive real number has a multiplicative inverse. Every means for all. For all real numbers, x. I'm just going to write for all x. We're just going to assume it's the real numbers. For all x, it has a multiplicative inverse, so I know there exists a y, so that x times y is equal to 1. Multiplicative inverse means you multiply them both together and you get 1. Okay, so that's the symbols. Now, let's deny it. So what does that become? For all x becomes, there exists an x, and there exists a y becomes, for all y, and then what do we have? It's not equal to 1. Does that make sense? No?
It makes sense. It makes sense.
It makes sense? Yeah, you're just negating it. Now you could have written that, if you're following along in the book, you'll notice that I didn't give. You could have also written this part in symbols a little bit differently. This is equivalent to this one. You have for all x, assuming x is greater than 0, because they didn't actually, oh, they did. Every positive real number. I missed that. X greater than 0. Every positive real number has a multiplicative inverse. It implies that there exists a y. X times y is equal to 1. I forgot the positive real number. I did. Every real number has a multiplicative inverse. This was every real number. So write it in symbols. It's for all. It should be P implies Q. This is the wrong, I did the wrong phrase. Sorry about that. I can't read. So for all x, x greater than 0 implies there exists a y, x times y is bigger than 1. So negate that. So negation of for all is there exists an x. Now, what is a negation of P implies Q? Where to write this? I'll write it right here. The negation of P implies Q is P and not Q. That's from our theorem in section 2 from last time, P and not Q. So that's what we're going to use here. This is P implies Q, so we have to write P down. So x is greater than 0 and not Q. So not there exists a y, x times y equals 1. So now let's do that and then it'll be done. So we have x is greater than 0 and what's the negation of there exists? For all. So that becomes a for all y. X times y is not equal to 1. Yep. Because that, you only changed the inequality right there.
Oh, I thought that was 0.
No, that's 1. Oh, it sure enough does look like a 0. It's a parentheses around it. There. That's the answer for that one. let's talk about example 26. Ran out of room to write it down, but let's actually do it in our minds. It says some children do not like clowns. So that means that you know that there exists a child the child and not likes clowns. There exists a person, I'll put it that way. There exists a person. The person is a child and not like clowns. So if you negate this one, then you know for all people, not either it is not a child, so it's not child, or likes clowns. And I used De Morgan's laws on that. Recall that De Morgan's laws, not P and Q, is equivalent to not P or not Q. So that statement would be, there are some people, or for some people, either they are an adult, they're not children, either they're not children, or they like clowns. That's how that one gets negated. Okay, we're almost done here. The existential quantifier. How many of you guys have written programs? Okay, that naughty, that exclamation point is not equal, does not equal, not equal, if that makes any sense. It is not the not equal to, the negation operator in programming. It means uniqueness. It's the hardest thing because when I saw that operator is after I had done programming. So for the longest part, and even from time to time nowadays, I'll read that as there does not equal X, and that's not what it's saying. It says there exists a unique X. So it's saying there exists a unique X so that P of X is true. And this is called the unique existential quantifier. This phrase right here in this theorem, it says if A of X is an open sentence with a variable X, then there exists a unique X implies there exists an X. If you know a unique X works, it still tells you an X works. The second one says a unique X exists implies that there exists an X so that A of X is true, and so this is existence, and for all Y and Z, Y equals to Z. This is uniqueness. Your last homework problem is going to ask you to negate there exists an X, there exists a unique X, A of X. So when you're doing the denial, there exists a unique X, A of X. That is going to be the same thing as the denial for this entire sentence right here. So you can parse through that denial and then see which one they give it to you as a multiple choice. You can see which one is correct. Only one of them will be correct. Okay, we are done for today.